Hi everyone, and in this video we are going to discuss about combinational logic hazards. Let's start. So what are combinational logic hazards? Boolean logic or Boolean algebra assumes that the variables remain constant during evaluation. This is an assumption, okay? It's logically correct, but functionality wise it may not be true during in physical implementation. The change of variable value or the change of literal value during the evaluation leads to incorrect answer. How can that change? It can always change, and that's what I'm going to discuss about later. For asynchronous circuits and combinational logic, for these circuits, hazards are very critical, but the synchronous sequential circuits are mostly unaffected, but depends on the scenario. There is a condition. If that condition is met, the hazards are not that important. Okay. Now let's understand what is a hazard considering a situation here. If you see this circuit over here, the switching equation is written over here at the down. As you can see, F is equal to YZ plus X bar Z bar. Okay. Now the circuit is implemented like this. Let's imagine a scenario where the inputs X, Y, Z are 0, 1, 1 initially. And when the input is 0, 1, 1, you can see that there is an inverter here and 1 comes here, right? As 0 will be inverted and 1 comes here. And Z is also, actually Z is 1. So the output of this thing is again, this is 0, okay? And this is 1, okay? So output of this is anyway 0. That's what written over here. And now this is 1 and this is also 1, so the output of this AND gate is 1. Any of the input is 1, the OR gate output is definitely 1, so you will get 1 as an output. Now let's imagine a situation where only the Z input changes. Okay, it's a legal nominal case where only single input is changing. There can be chances that multiple input changes, which is other type of issue which we may discuss in some future videos. But now imagine only one input is changing at a time from 1 to 0. So the next out input is like 0, 1, 0. Okay, so what changes? In fact, here, see, when this becomes 0 and this is still 1, the output of AND gate is any one is 0 means output goes to 0. The arrow shows the next output, which is this Z is 0. Okay, but and what we expect from here is the Z is 0, which means the actually the input to this AND gate is actually 1 since it is getting inverted here. So both inputs are 1 here, 1 and 1. The output is 1 from this AND gate, and if any one of the input is 1, the output of this OR gate is 1. So output stays at 1, 1, and the next output is also 1. So what's the problem? The problem is that this combinational logic does not account for propagation delay. So if you can see the path of input, path of this Z input to this AND gate and the path of the Z input going to this AND gate, those are two different paths, and the travel, the propagation delay of this path looks more. The reason is that there is an AND gate over, sorry, there is a NOT gate over here, and there is a transition time, right? And that has to be accounted. So it's most likely that this path is will take more time than that of this path. Okay, so what can happen if this path hasn't reached that means this signal Z has reached this AND gate first, which means definitely this will output to 0, and this signal, which is 0 of this Z, hasn't reached this input yet, which means it hasn't reached here. So the input of this thing is actually 0 itself, which because the previous input was 1 from Z, So it was inverted and given 0 0. Sorry, it was 1 and this was 0, so it was 0 again. So both the inputs were 0 and output momentarily switches to 0. And when this 0 reaches here, okay, when this 0 reaches this place, definitely it will switch back to 1, which is what is expected. But as you can see, if this 0 hasn't traveled here quickly enough, that this signal actually outputs to 0. I mean, this signal already becomes 0 and this is evaluated. This um, OR gate is already evaluated and sent forward. Then the output of this OR gate momentarily switches to 0 and then comes to 1, which is not supposed to happen. And these type of very small width momentarily switching signals are called as glitch actually. So this is what is called a hazard, which is not supposed to happen but happens because of difference in propagation delays. So we will try to understand more about glitch. So glitch is an unwanted short pulse, as I told you, and glitches may not be a problem or may create a havoc or large devastations. What do I mean by that? Sometimes glitches are not a problem at all because it depends on the scenario how a glitch is transformed into. Okay, so if we so the next sentence says that if we delay the evaluation until all propagation delays have transpired, which means they have completed, then the hazards are not a problem. What I'm trying to say is, let's say we are evaluating this see, this combinational logic might be sent to somewhere, or sensor is reading the input from this OR gate, or some logic or flip-flop is uh, reading the input from this OR gate. If the flip-flop takes the input from this OR gate after considering all the propagation delays, the worst case propagation delay, then okay, it's fine, which means it is taking consideration of this propagation delay. Okay, let's imagine that, let's say this, the worst propagation delay is this one, and let's say it is some zero point 0.5 nanoseconds, and after so we are, if this flip-flop or something is reading the input from this output of this OR gate after 0.5 nanoseconds, it's fine because it will read the right value. Even though it momentarily switches in between, it's fine. But what if it reads before? It may read 0, which is not actually supposed to happen, right? So sometimes if we are evaluating, then it's fine. If we are evaluating after the propagation delays are transpired, but if we are not, it's a problem. Okay, so if circuit speed is less than the hazards, it's not a problem. This actually, this above sentence boils down to this final summary, which is, if the circuit speed, which we are speaking about in terms of what we can call a flip-flop to flip-flop, a register to register path, if we consider, then a clock is controlling that logic. Okay, and if the clock speed is less than that of the hazard, which means it has more delay. Okay, so that's what I just told you. If the zero point 0.5 nanosecond, if this is zero point 0.5 nanosecond, the worst propagation delay, and the clock speed itself is lesser than that, which means the delay between the two, the pulse width of the clock, or the period of the clock itself, is more than zero point 0.5 nanoseconds, definitely it's not going to be a problem, because after zero point 0.5 nanoseconds it's going to be red. So what went actually wrong with this circuit, and do we have any solution in this way? Yes, we have, and let's understand what solution we have. Okay, and what went wrong. Okay, so if you see that switching equation, which is yz plus x bar z bar, we can write it in the canonical form. It looks like this, and let's write it down, and let's make a Karnaugh map out of it. Okay, so if you see the Karnaugh map, so it's exactly same as this actually. X bar, y bar, z bar, which is 0 0 0 over here, we made it 1, and x bar, y, z bar, which is 0 1 0 0 1 0, this is 1. Okay, and we have x bar, y, z, which is 0 1 1 is 1, and finally XYZ, okay, which is over here 1 1 1. You see this one, right? Exactly same. The equation was logically perfect. Okay, it didn't have any issue. But if you see the prime implicants, where, see, while minimizing this Kernoff map, what we did is we grouped this thing as these two as one, and this one and this one as another. Okay, there is an overlapping group here, okay, which I showed it in the dot lines. So if you see that, it looks like it's not needed, right? So that's why we say essential prime implicants are just YZ and X bar Z bar. But if we lose that information, and this is what is going to happen, the hazards may get created. So if we include this X bar C bar plus X bar Y, if this additional X bar Y is included, this overlapping group is included, then the equation would look like this: X bar Z bar plus X bar Y plus YZ. Okay, and finally, here we have a circuit. Let me move it over here. So here we have a circuit where we have included all these things with this equation. Now, if you see this situation where this Z turning from 1 to 0, even though this Z turning from 1 to 0, what happens is there is another AND gate which is taking input from this Y and this X bar, which means actually X bar is staying 1 and Y is also staying 1 when only this is switching, right? Only this is switching, so both of them are 1. So output of this was definitely 1 of this AND gate. So indefinitely the output is staying 1. So this circuit is staying away from hazard. So it's a hazard free circuit. So this is how we can solve the problem. Okay, that's the reason why we should have this also as a group, whichever the overlapping thing is. So finally, we will see the classification, the types of hazards. There are two types of hazards mainly. One is called static hazards and one more is called dynamic hazards. In static hazards, the one example that I showed you is actually a static hazard, but it is a static one hazard, which means the output was supposed to be 1, but momentarily goes to 0. And it can happen with min terms, which is like sum of products. Okay, this is an expression which is sum of products, right? X into Y plus Y bar Z. So the static hazards are mainly like these hazards are produced when the outputs are in steady state. Okay, so the static zero hazard is the other way around. The output is supposed to be 0 but momentarily goes to 1, and this can happen if we make a product of sums. Okay, so finally we have dynamic hazards. The output changes 3 or more times or multiple times when it should change only once during the transition. So which means what I'm trying to say is, if the output was supposed to be 0 to 1, let's say there was supposed to be a transition from 0 to 1, but it is like 0 1 0 1 0 1, like that. Okay, it's switching multiple times to reach that point from 0 to 1. That's all. So this is called as dynamic hazard. The reason why this dynamic hazard happens is, so it's independent of static. Okay, a circuit may be a circuit static hazard may be completely clean, which means let's say we have taken these things into consideration as well. Okay, but there can be a situation, what happens is, now we have assumed something here also, which means we are assuming the AND gate, the gates here, AND gates have same transition time, or the speed of these AND gates are same. We are assuming that, but which may not be true in reality. All the AND gates may not have same transition times. We call them timing arc in static timing analysis. Let's not go too deep into that, but anyway, the timing arcs, or the speed of this gate may not be same for all the gates. Okay, because of that difference in speed of the gates, this gate may be faster than this gate. This situation of dynamic hazard can always happen. Okay, So this is exactly the same situation. The output goes momentarily to another state, but it's because of some other reason. It's because of the cells, the transition times of the cells itself, that there is a difference. So because of that case, the output may switch multiple times, and finally it reaches to the place where it has to reach, whether it's 0 to, if it has to reach logic 1, it will reach logic 1. It will have, if it has to reach logic 0, it will reach logic 0, but through multiple steps. That's all is going to happen. So this is what the classification looks like. So these are the two types of classifications. So I'll try to keep this PPT in this description. You can download it and later use it for your reference. That's all for now. I'll see you in the next video. Thanks a lot for watching, and bye bye.